I'm starting the recording. So let me start now, and when people join, Prafula will admit them. So thank you for joining me today. Last month we talked about the DeepSeek model, the DeepSeek V3 and R1 model, the model from China that tried to do as well as OpenAI O1 model. And one of the key ingredients in the DeepSeek was reinforcement learning. I didn't spend too much time last time, so I thought that I try to spend a bit more time to explain what is reinforcement learning and how it is used in reasoning models. Okay. We'll have time for questions at the end. So if you have questions, just write them down, and we can address them. So the outline of this presentation. So I'll go over basics of the LLM models, talk about reinforcement learning, then pre-training of LLM models, then the post-training. So this is like the new thing. Talk about thinking or reasoning. I assume it's the same. Then how reinforcement learning is used in these LRMs. So LRMs are for large reasoning models. So let's start. So this is a very well-known leaderboard that compares chatbots, LLM models that you have. So here it is. So I looked at this ranking today. So you can go to lmarena.ai, and you see that number one is the Gemini 2.5 Pro model. From Gemini, Google Gemini, from Google. Number two is Grok 3 from xAI. Then OpenAI's GPT 4.5. So, and this ranking is changing very often. It's based on pair comparisons of so the votes people have so when you go to this website, you can also vote. You are faced with two chatbots. You don't know you have chatbot A and B. You interact, you ask questions, and then you vote which one you prefer. Right? So is how they rank them. What is interesting, the last column, is that you see that the top models tend to be proprietary. Means that they are they're usually owned by private companies, and they are not. You don't share all the details of these models. I mean, we know overall how they work. We don't necessarily know all the details. At number 7, we have the DeepSeek R1 model. Right? It's interesting that so this one is open source, and you can download. You can use it freely. And then the next one will be Gemma. So Gemma is an open source model from Google. It's quite interesting, at least that as of today, there's no non-Chinese open source model in the top 10. The O1 models is around 7, so that kind of the same ranking. So DeepSeek R1, I talked about it last time, so I just wanted to mention that the reinforcement learning is a big component of DeepSeek R1. So it's applied to the base model. So base model means that the generic LLM models that is not specialized in fine-tuned for reasoning. And the DeepSeek model can show reasoning skills. Or maybe I should also remind you to clarify what reasoning means. Reasoning for LLM models and reasoning for humans is maybe not exactly the same thing. So when people talk about reasoning or reasoning models, it means that when you interact with the model, it takes more time and it gives more details in how it comes out with the answer. Okay, so if you you say you ask the model to solve an equations, like quadratic, x squared plus 4x minus 3 is equal to 0. Then it's not going just to give you the answer. So this will be the traditional model, but a reasoning model will tell you, okay, I try to factorize the equation, or I put the 3 on the other side, and then it gives you all the intermediate steps and give you the answer. So typically it can take like 10, 15, 30 seconds, sometimes minutes, sometimes 10 minutes to come up with the answer. Is what we call reasoning, right? In that context. It doesn't mean that the previous model don't reason. This is how I think it is the convention. And maybe it's more convincing that it is reasoning if you see the details, right? So DeepSeek R1 can do that. DeepSeek V3, the more like generic model, doesn't do that explicitly. So let's talk about reinforcement learning. So it just happened that as I was planning to give this talk, the two giants in the field of reinforcement learning, Andrew Barto and Richard Sutton, received the Turing Award. So this is the Nobel Prize in computer science for their work in reinforcement learning. So they're very well known in that field because, well, they contributed a lot, but also they wrote a very useful textbook called Reinforcement Learning that you can find on the internet. This is the second edition that gives you all the basics of reinforcement learning. I think they're probably both retired. At least Andrew Barto is retired. He used to teach at UMass Amherst, and Richard Sutton is still a professor at the University of Alberta. Okay, so the Canadians are very good in AI. In fact, they have good centers in Alberta, Toronto, Montreal. So it's almost like a Canadian specialty. So reinforcement learning has been recognized by the Nobel Prize in computing science. So what it is? So if you never heard of it, it's the idea is relatively straightforward. So it's really based on so it's at the intersection of many fields. So it's computer science, obviously, machine learning, operation research, applied mathematics, psychology, cognitive science, game theory, economics, and finance. So why psychology? Because it's just the hypothesis, the driver of the model is that, like here will be an agent or a person or an animal, like say a dog, could be motivated by a reward, right? So you can give a sugar to a dog, and so you have these, there's experiments in psychology. You give a reward or give a punishment to try to motivate a behavior, right? So reinforcement learning has the same idea. So basically we apply it to AI, like entities, robots, or agents or AI models. This is what we call agents. So we take a series of actions, right, to maximize an expected cumulative sum of rewards. Right? So it could be, in economics, it'd be a monetary reward, but for a program, it could be just like +1, right? Say each time you do a positive action, you get +1. If you negative action, you get 0 or -1. Okay, and the agent will try to behave, take decisions so that it maximizes the cumulative sum of reward over a time span. So they're like 50 rounds. You'll try to get +50, right? This is the maximum reward it can earn. The reward can arrive immediately after an action or much later, right? Because say you play a game and then you get a +1 if you win the game, you get 0 if you lose the game. So the reward will arrive only at the end. Or it could arrive at each round, right? There are like 50 rounds and you get a +1 each time you win a round. There's typically a discount factor. Discount factor, what it means that rewards earned later in time are less valuable, right? And so this is what we call this discount factor. And reward that we earn right away is more valuable. So it should be usually a time discount factor. It could be that it could be a probability of not finishing the game, or so just something that a reward that is given to you in 1 million years is probably less valuable than the reward I give you like today. Okay. So the reward tomorrow is worth less than the reward today. So yes, that is not necessarily military payment. And so to get rewarded, the agent has to take an action. Right? So we call AT. And let me do something. Okay, something cool I wanted to use. Yeah, the action AT. So it takes an action in response to a state on the environment. So so for if the agent is playing a game of cards, it depends on its the cards it receives, what is on the deck, etc. If it's a video game, it'll be the other like players in the games and etc. So after the agent takes an action, he receives a reward. If if he can receive a reward, he might not receive a reward if he has to wait longer, and the environments will change to another state, right? So it will transition from one state, right, ST. So you see the environment has a state ST, right? T is the time. The agent receives that information, take an action, right? And then the environment is changing to state ST +1, right? And then there's a loop, okay? So the components, so I'm not going to use, maybe this is the only equation in the presentation, right? So don't worry, but just want to give you the vocabulary so that you can a bit follow the people in your head, or you want to read a paper, or you read the textbook from Sutton and Bartow. So we'll talk about this. So just so that you're aware of the components of reinforcement learning. So first, they talk about a Markov decision process, MDP, right? Markov decision process. So this what represents the state of the what represents the environment, right, of the agents. So on what we call an MDP model, so that has this Markov decision process, will be defined by a state, set of actions, some transition dynamics. Transition dynamics is what moves from ST to ST +1, right? So how the environment is changing. Gamma would be the time discount factor, and the reward function R. Okay, so it would be S, A, P, R, and gamma. Right? So this would be the Markov model. So each period of time t, the environment is a state ST. The agent takes an action AT and receives a reward R of ST and AT. Right? It will depend on the action and depend on the state. Right? And then a new state ST +1 occurs right after the action is taken. So that's what we've seen previously. Okay. So we said that ST has the Markov property, right? If the future state ST +1 depends only on the current state ST, okay, but not on any previous states. Okay, this is what they call the Markov property. It makes the modeling much easier, right? If you know the state of today, you can predict the state tomorrow. You don't need to know what's before that. And then the dynamics. The dynamics is modeled by the transition probability P. So given the state S and the action A, it produces the state ST +1 with some probability, right? So it could be deterministic. It means that this will be 1 for a particular ST +1, right? Or it'll be probabilistic means that you forecast so it will be a distribution. Okay. And if it is discrete means that you have like it'll be you have the different state S1, S2, S3 is not a continuum. Then it'd be the P, the transition will be represented by a state transition matrix. It could be a matrix. Okay. So given all this, given that that market decision process with these parameters, an agent wants to maximize its cumulative lifetime rewards, right? And it's going to do that. Is going to use a strategy, or here in that they use the term policy. Right? In game theories, we call it strategy, but here we call it policy, right? Has a policy. So how I am going to act, right? On produce my action given the state, right? And I'm going to then produce a state value function, right? What will be the value, my future, the present value of my income today, a state action value function Q. Q is also a value, the cumulative sum of awards given my action, the action today and the state today. Okay. So we saw the policy. So the policy can also be stochastic, right? So you can be deterministic. Say, okay, for that given state, I'm going to do that action for sure, or I can perform some action with some probabilities. Okay. So the state value functions, the expected cumulative sum of rewards, right? See, when we follow the current state is S, and the state value function is Q, right? And the expected value cumulative sum of rewards that the agent will receive, the policy is followed starting from state S and action A, okay? But the whole game of reinforcement learning is trying to maximize Q and V, right? By changing P, right? The pi, sorry. And the policy, right? So you try to, the agent has to decide what is the best policy so that he can maximize the rewards. So really the thing that you have to remember. And here it'd be just like the sum of reward. So it's just like the reward I receive today, I receive tomorrow, I receive till time t, right? And you see the discount factor gamma is typically a number smaller than 1. Okay, it could be 0.8 or something like that. And as you see, because it's a factor of t, a number lower than 1, you multiply by itself many times, it tends to go to 0. Right? So this is why that action like closer like to today are more important than actions and rewards that we have done later in time. Okay, so you have to remember V and Q. So here, okay, so that slide is a bit heavy, but so this is just the policy. Maybe I won't go into too much details here, but the policy is that, so I said we have to find what is the best policy, right? So when we talk about the policy, right, given action, what's the probability that I'm going to take the action A, right, given the state S, okay? But that policy, the agent can design the policy, can choose, okay, how I'm going to act. And it is parameterized by a parameter vector theta, okay? So it's a probability I'm going to do action A, given the state S. I'm going to optimize theta, right? So that I get the best policy, right? And usually the optimal theta will be found by iteration from a gradient of the objective function. So what is a gradient? A gradient is that, in calculus, if you have one variable, maybe you remember from school, that you have a function, you want to try the maximum, or you want to see if it's going to increase or decrease. You have to calculate the first derivatives, right? We take a differential of between around 2 points, so to measure the slope of that function. So the gradients is the same thing when you have like many variables, right? So it's a bit like a derivatives, but with many variables, because the theta can have like several dimensions. Okay, a policy can be, it really might not depend only on one parameter. Right? So you have a gradient. So you have the objective function will be the value, right? The value function, and you want to try to maximize it. So how do you maximize it? You compute the gradient. So usually it'd be a delta J, okay? So with respect to theta, right? And the optimal parameter vectors are going to be found by iterating theta t plus 1 is equal to theta t plus a step size parameter multiplied by the gradient. Okay, so the gradient, because you have the gradient, you also, do I need to increase the parameter or some dimension of parameters slightly or decrease it to get closer to a higher value of J? Right? This is what you want to maximize, right? So the gradient in that, in machine learning, they talk a lot about the gradients, about policy gradients. So this is what they're referring to, right? So the gradient, so here it says one variable, like in one variable. The gradient is positive. It means that it's an increasing function. So you want to increase theta, right? So the gradient positive means that you increase theta, it's going to increase J. So you want to increase theta at each step. If it is negative, it means it's a decreasing function. So it means that you need to decrease theta, right? To increase the value. So there are many methods to do that. I'll mention some of them towards the end. So you'll see things like TRPO, trust region policy optimization, PPO, proximal policy optimization, deep deterministic policy gradient. So there's a huge, field of research specialized in this. Try to find what's the best way to find theta. Right? The end game is just to find how to manipulate these gradients to find the theta and to get the best policy. Okay. One last thing, I think this is really more for if you read the textbook, you'll see that it get mentioned a lot. I'll just talk about what we call more like policy-based methods, right? So first, there's two terms we call like model-free and model-free reinforcement learning and model-based reinforcement learning. So the difference is that in model-free reinforcement learning, we don't know the dynamics of the state. We don't know how the environment is changing. That's what we call model-free. So we don't know that these transition probabilities from one state to the other. When it's model-free, we don't know that, right? The agent doesn't know that, and it doesn't try to learn that, right? Model-based means that we know that dynamics. Right? So there are three approaches to solve the model-free RL problem. One would be value-based. So the values, remember, you have this V and this Q, right? So we want to evaluate the value function. So the state value function V, the state action value Q is evaluated, and you have algorithm trying to find better to estimate V and Q. This is the value-based methods, right? And the action use V, try to estimate V or Q, and then based on that, try to plan her action, right? You choose the action that will maximize Q or maximize V. Policy-based method, this is what we mentioned previously, is we try to find pi directly, right? I try to find that policy function directly, or at least to find the parameters theta so that you increase the payouts. Actor critique method is a combination of both methods, where we evaluate both a value and a policy function. Okay, so we have a model that estimates the value function, right? The V or Q. It's what they call usually the critique, right? And then you have another model that tries to evaluate the optimal actions, right? That function pi that we saw before, the policy, and what we call the actor, right? So the actor means that the actor is the person who's acting, right? Who's doing the action. So the name comes from that, right? So the actor controls the policy. And the critique tells the actor, is it what you are doing? Is it increasing the value or not? Right? Is it increasing the payoff or not? It is somehow the critique or the we call the coach or the advisor that say, okay, your action is great or not that great, right? And it gives the feedback on the value, right? So that's why that this graph is a bit. So you have the environment, the state, it gets sent to the critique and the actor, right? The reward is paid only to the actor. The critic doesn't receive a reward, but the critic gives the value, an estimate of the value, the sum of cumulative reward. Okay, and then based on that, the actor choose another action. This is what they call actor-critic method. Okay, so just a couple of examples. So this has been this reinforcement learning become very popular thanks to Google DeepMind. I mean, of course, with Sutton Alberto did research on reinforcement learning, like for many years before, even many years before DeepMind it was even created. But the DeepMind team used reinforcement learning to its Go playing model, AlphaGo. Okay, so AlphaGo was the first program to achieve a superhuman performance in Go, and it used like an actor-critic method, what we discussed the previous page, a policy network, how to play the game of Go, and a value network that say what is the likelihood they're going to win the game or not. Okay. So the policy network was trained by supervised learning, so it means that it had example to follow. So the first version of AlphaGo, they recorded the gameplays of professional like Go players and champions and tried to imitate these players. So, okay, given the configuration of this board, the best players play that, so they're trying to play the same. So that they train the policy of AlphaGo. Okay. And then they did some refinement with the policy gradient, like reinforcement learning. And value network is trained to try to predict the winner of the games, right? Of the game. So are you going to likely to win or to lose? So they have reinforcement learning. And then another like innovation is what they call MCTS, Monte Carlo tree search. So this illustrated here. So it's really like so what's trying to do? Monte Carlo means that these are like you simulate some path forward, right, of possible strategies, right? So you do simulate many of them. This is a tree because it starts from like the game, the position, the boards today, like as it is now, and then do some simulation. So it looks like an inverted tree, right? It's like this, so it's called a tree. Monte Carlo because you have simulation, and tree because it has a shape of a tree, right? So it explores. So it's a bit like when you play chess, right? You think in your head, okay, if I move my knight, I move my bishop, and so on, how is it going to do? Then the opponent is going to do this, to do that. So you simulate in your mind. So you do some kind of Monte Carlo tree search, right? When you think. So the computer, the AlphaGo, is doing the same. So it has like 4 steps. So it simulates some strategies, right? So it goes then you have selection, expansion. So you get to see like try to go deeper, right? Like to do like simulate different game different steps. Then you try to evaluate, see am I winning or not? I am in advantage or not. And then it has a backup that try to learn the lessons from this, right? Is it a good play, a bad play, right? And then based on that, you're going to they're choosing the optimal game, okay? Optimal play. AlphaZero is very close to AlphaGo. The only difference is that with the notion of cell play, right? So it's using also the same reinforcement learning, exactly the same thing, but it's playing against itself. Okay, so it's playing against itself. So you remember you have this policy. So it usually will play against a version of itself that has a slightly older policy. Okay, so each time you play, you have a new policy, but you play against an older policy, and you try to improve it iteratively. Okay, but you still try to evaluate the policy network on a value network. You get the same, and then at the end, you evaluate the policy because you know if you won or not, right? The computer is going to play against another version of itself. It's also using the same thing in terms of Monte Carlo tree search. Select, expand, evaluate, and backup, right? And decides to play. The last example from DeepMind is so hey, it's more complicated, so I won't go into much details, but this is also used for so AlphaGo. You say okay, it's 2 players. Is relatively, I mean, Go is complicated, but the rules are quite simple. AlphaStar, this is a video games, I think, based on StarCraft. So you try to teach an AI to play video games, right? Which is not trivial, right? Because you have many options. The environment is very complicated. It's the environment of that video games, and you have a lot of players. You have like a lot of like other players around you, and you have a lot of decisions, right? So and still you can apply reinforcement learning here to teach the model how to play this game, right? So here probably they mentioned supervised learning. So it's very likely that at the beginning they also try to learn from the best players at StarCraft, right? Try to mimic them, and then progressively like use a reinforcement learning model and reward the model when it's winning the game, or maybe it gets more points, and then it adapts its own policy and decides what to do. It's kind of remarkable that it's able to do that. Okay, so this is a reinforcement learning. So for large language models, so if you have seen like presentation like this before, you heard about that large language models are typically they try to predict next words or next tokens. At least they're trained to predict the next tokens. Right? You say like, oh, the robber or that person robbed the bank. Who is that person? Right? So then you have to the prediction would be like it's a robber or like a criminal, right? But you say my boat is reaching the river bank, right? The model has to understand that bank is not the same as the first bank, right? And you can ask a question and it will answer the question correctly in the context of a boat reaching the bank. Okay, so this is what they're trying to so all these like ChatGPT, GPT-4, and so on, they're all trained like that. So they use what they call like a technique like transformers. So transformers is a techniques that the model can understand the relationship between words, right? Between like robbing a bank or like a boat reaching a river bank. So all these things it can memorize and learn the subtlety of human language. So with this, they can develop a broad and generalized understanding of language and information, right? And interact with us. What is remarkable is that they benefit from what they call scaling laws, right? So more tokens and more parameters, mean like bigger models, more like more neural networks in the models, trying to improve performance, right? More tokens just means more words or more data, right? So the data will be a typical like data set that this is used by the model from Facebook, from Meta, the Llama model. So these are the kind of data it's using. So they tend to be collected from the internet, Common Crawl, C4, GitHub, Wikipedia, and so on. You see that these are like huge 3.3 terabytes of data, etc. Wikipedia is like 83 gigabytes of data, archives, etc. Then in terms of the model, you can see that these models at the time when it was published in 2023, you have like some models would have like 65 billion parameters, but now you have some models have trillion of parameters. Right? So probably the latest models have over a trillion parameters. So they have huge dimension, and these are heads and so a number of layers of neural networks. So usually the bigger the models, the better they perform. And also the more data they use, so it's a billion of tokens. And these are what they call training loss. Usually you try to minimize the loss. Like you have an objective function, like say accuracy. So you try to, this curve has to be lower. So the more data you use, the better the performance of the more you can calibrate, the better you can calibrate your model. But the problem is that we're probably running out of this, right? The internet has a finite size, at least in terms of words. You might be like, exhausting all the available tokens on words to train these models. So now come like post-training. So post-training is not like exactly new, but post-training is becoming more complicated or richer, if you want. Right? So post-training means that I run all these like giant like neural networks, right? But then I have to the model is not ready to share, right? Or to sell to customers or to put it on the internet. It needs to do post training. So it's like these are the additional learning stages after the initial pre-training to make the models more specific, more specialized, right, to particular task, aligned with human preferences, so that it sounds like it gives the answers that humans like or prefer, and safe and controllable. Right? So you don't want to have a model that is that is rude or say like nonsensical things or so on, or curse or this kind of things. Right? So you have to kind of clean up the model so that the model looks is usable. So you have this post-training approach, what we call like so one would be the fine-tuning. So you specialize the specific data set. So it's used to be used by lawyers, by doctors, and so on. You have like specialized data set, specialized examples. You will fine tune. It means that you calibrate the model, typically a subset of parameters of the model, try to calibrate on this specific data set. And instruction tuning means that when you interact with ChatGPT, when you ask questions, you ask things to ChatGPT, right? So usually the ChatGPT is trained to understand what you're asking. Okay, so this is what we call instruction tuning, and you typically have to give examples of instruction, right, and examples of good answers, and then the model is trying to follow that. Right? So so here this is one example task instruction. I won't go over this too. This is let's say a typical like input given utterance and recent dialogue context containing past 3 utterances. Output yes if the utterance contains a small talk strategy, otherwise output no. Okay, then you give the examples on the negative examples. Okay, then you try to find so typically you give the questions, you see like this is a good answer, this is a bad answer, and the model tries to learn from that. And typically it's learning it from using reinforcement learning. Right. So this is reinforcement learning from human feedbacks. Right. So I'll go to the example. For instance, so for instance, we want to try to teach the LLM to be polite and helpful. Right. So if I just like train the model, it will be the initial base model behavior. For instance, the questions with the prompt, what you enter into the, let's say, ChatGPT, can you help me understand quantum physics? Right? Then the model says, quantum physics is complicated. You probably won't understand it. It involves weird particles doing strange things that don't make sense to normal people. So forget it. Right? So then you say, wow, this is not a good answer. It's not, you don't want ChatGPT to say that to users. Then you have the humans. You have like someone who's going to look at the answer, what we call a human annotator. There are people who are paid to do that, to review like output of AI models, and we'll rate the response, right, as unhelpful and condescending, right, and we provide an example of a better response, right, and there will be an example, it will be like a better response. Quantum physics explores fascinating principles about how matter and energy behave at the smaller scales. Let's break it down step by step. Would you like to start with some basic concepts? Okay, so when you use ChatGPT, you use whatever chatbot, you are used to this kind of answer, right? You see people, usually these chatbots are polite, they're nice, they don't. So it's because it gets scrubbed, it gets cleaned by this human feedback process. Okay, so the next step is that all this feedback that you collect is used to build what we call a reward model, right? That learns to score the response based on politeness, clarity, encouragement, depth of explanation, accessibility to the users, etc. Right? And then once the rewards are built, right? So that answer will have a high score, it will have a low score, right? Then it's using what we call like reinforcement learning fine tuning. So reinforcement learning, right? You have the reward, then the model can choose different words, different answers. This is action, right? And try to get the answers that gets the highest scores or the highest rewards. Right? So that's how you train. And then the final answer will be quantum physics will be this one, right? So you see that it be quantum physics is a fascinating field that explores the behavior of matter and energy at macroscopic scales. It may seem complex, right? Maybe we can break it down into understandable parts. We'd like to start with some fundamental concepts that can help demystify this exciting area of science. So it's much better, right? It's a kind of combination of the human gave us feedback and the bad response from before. Right? So this is like reinforcement learning from human feedback. So let's talk about thinking or reasoning. Right? So this is an example of so this is using a DeepSeek R1. So hey, you can download DeepSeek, right? It's open source. You can run it on your computer. So it says I've been running it locally. So the question is, so one question is a math question. So Alice and Bob each have a coin and flip it until they get a head. Okay. If Bob flipped his coin more times than Alice, what is the expected number of times Alice flipped her coin? Okay. It's not trivial. No, I don't know. You can try. You can see. By the end of the talk, you can see if you can find the answer by yourself. So it's not trivial. But I mean, the question is clear, right? They flip a coin. Bob flipped his coin more times than Alice, and they stop when someone gets Alice or Bob gets ahead. And how many times Alice has flipped her coin? Okay. Is it 1, 2, 3, 50, 100 times, 1 million times, or never? You can find it out. So I want to go over the thing, but this is the answer of DeepSeek R1. Okay. So it's on the answer, I believe, is like 4/3, 4/3. But it doesn't just say 4/3, right? Say, okay, I'm trying to solve this problem with Alice and Bob and so on. Let me break it down. So they describe the context. Both Alice and Bob are performing the independent tries. Fair coin, the probability is half. So he puts the phrase. So this is all the model output, right? And then it does all this calculation, right? So I'll go over this. So okay, more calculation, right? More calculation, and then he finds the answer, right? And then okay, so this is up to now. This is the thinking, right? So so we see the output, right? It tells you, okay, this is what I'm thinking. And then, okay, this is I found the answer. And then you give the final answer, right? So it's like, when you take a test, sometimes you take some scrap paper, you write it down, say this is how I'm going to solve it. And then you write the final answer. So it's doing the same thing. And this is the final answer. It gives you all the steps. This is a clean output. Okay. The notation is a bit from LaTeX. So the answer is like 4/3. So this is what we call about reasoning and thinking. So it looks like thinking and reasoning, right? It looks, if you're like a student and someone come up with all these things, I say, wow, that person thought a lot about to get the answer. And usually in math, or a student, you ask a question to a student, the student usually you cannot give just the answer. You say, okay, how did you come up with the answer? Right? Give me step by step, like give me your reasoning step. And for instance, when you have your paper graded, you don't get full mark. You just give like 4/3, right? You have to give all the steps. So the DeepSeek is doing exactly that. Right? It gives all the steps, and probably you get a full mark for that. So this is related also to system 1 and system 2 thinking. I think I mentioned this before. It's not exactly the same thing, but so system 1, system 2 thinking is something introduced by the psychologist Daniel Kahneman. He's one of the rare psychologists who earned a Nobel Prize in economics. He's not even an economist, but he got the Nobel Prize, I think, before. So the system 1 is the quick, intuitive decisions and actions. Right? So when you don't think, you just come up with the answer, the system 1. Does that mean that it's wrong? Right? Because many of your decisions, maybe 80% of your decision that you do, the wake up in the morning, take your breakfast, it's just system 1. It's like routine, right? You have to think hard to make the decision. System 1. System 2 is it's more slow, thoughtful, logical. So once you find the answer 4/3 from the previous questions, really you have to use system 2, right? It's unless you're a genius, you won't be able to use system 1, right? You have to do system 2, more deliberate thinking, write it down, so more like a thoughtful, right? So the analogy, I don't know if I really agree, but we said that the pre-trained model is system 1. ChatGPT will just give you the answer right away, or just in a second. The post-trained reasoning model is more like system 2 because it gives you all the steps, and you can take time, you can take 10 seconds, 20 seconds, 30 seconds, right? So this is like a comparison. So this is from Claude. The analogy is not really correct, right? Because LLM models, even ChatGPT can give you answers that look like system 2, even if it gives it very fast, right? So it's not really, it may not be exactly correct. And brains and LLMs are not, even though we talk about neural networks and so on, probably brains are maybe more complicated in their own way. Okay. So reinforcement learning for reasoning models. This is from a recent survey. So we are really like focusing on this area. Right? So here they're talking about what happens after training. A lot of things can happen post training. So I'm going only to focus on how we use our reinforcement learning, reinforcement learning. So here you recognize RLHF, right? Reinforcement learning with human feedback. AIF, I didn't talk about it, but it's just feedback from AI, right? Then PPO, XTRPO, and so on. So this is what we're talking about. And the other things are like, there's a bit of Monte Carlo research here. So the way we use it for LLMs, so you remember you have a state, right? The state will be the sequence of words, the tokens generated by the LLMs up to now. Then the next step, the ST+1 would be like what then the next the action will be the next token or next word, right? That is going to predict. The reward will be the quality of the output, right? So it could be based on human feedbacks or other feedbacks, right? And the policy, right, is to maximize the expected return, the sum of like qualities measured, would be like measured by a number, likely. So in order to have the best quality output, right, by producing each token. Okay, this is how reinforcement learning is framed into LLM. So here these are like all kind of from the same survey. I found that table quite interesting. So there are all the different models. So here you see DeepSeek R1, you see Claude from Anthropic, Gemini, and so on. You see what kind of reinforcement learning methods that they use. Reinforcement learning for human feedbacks, usually you try to find it a lot. You have PPO and so on. And in the fine-tuning step, the kind of things that they use. Okay, so you see that it is used extensively. So I give you just some things that they use for reinforcement learning. I won't go into too many details, but there's one thing, that notion of PRM and ORM, process reward models and outcome reward models, right? So outcome reward models means that you get, remember when I described reinforcement learning, I said you can get a reward only at the end or along the game. So this is the same thing. Process reward models means you get rewards during the process. So when you do reasoning, right, you get reward for each reasoning step. So each time your reasoning one step is correct, you get a reward, right? And so this is like the process reward models. And usually it's done by a human will overview the reasoning process, and a more powerful model will review the reasoning process. Outcome reward means I only give a one, a good one if the answer is correct or not, right? So if 4/3, I give a 1, and I give 0 if it's not 4/3, right? For the answer of the math puzzle. Reward process, I give a reward of 10, and 1 if you achieve like, okay, talk about this, talk about that, it's clear, it's logical and so on. So here, and then I give like a sum of rewards. That's the process reward. So there are different ways you can reward this reasoning. So here there are different. So this is a huge literature. So I just mentioned something called like OpenRFT. So reinforcement learning, fine tuning. So you try to do exactly that, right? Try to find how to build, how to use, how to implement reinforcement fine tuning. And the tricky point is how to build the rewards, right? We talk about outcome or process reward models. Okay. Something I want to mention is that something that came up from OpenAI, December 6th, where they have also what we call a reinforcement fine-tuning research program. Then they want to collaborate with researchers, you could be interested to do that. And what they want to do, what OpenAI wants to do, they want to specialize the models into like different verticals, right? To be like very good at one particular point. They don't want to collaborate with experts or researchers to do that. And we know that we can do that with using reinforcement learning, reinforcement fine tuning is what they do that. So typically what you have to do is like experts have to come up with some reasoning task on the right answer, right? Let's say, okay, I'm a chemist. I want to produce this matter, this component, and then I need to do all these steps. So the OpenAI wants to collaborate so that they can build these like expert models that after that they can share and distribute. Right? Okay, I'm going to get close to time, so I just mentioned I won't go to too much details on this, but you have PPO that you find very often. PPO is a gradient, a method to get the gradients to optimize the policy. So it's optimize the policy while ensuring that the new policy doesn't deviate too drastically from the previous one, right? So you have like new observations, new tokens. You train on new rewards, new feedbacks. You try to train the models, but you don't know policy that is like going up and down, or this is like very volatile. So that's what you do. You try to stabilize. You can say, okay, you can get a better policy, but it shouldn't deviate too much from the previous policies. This is what really the main idea was. So try to estimate that pi, right? That pi functions, but to make it so that it does it progressively. Right. GRPO, I talked about it last time when I described DeepSeek. Is what so it's a variation of PPO. On what they're doing by batch of observations, and they try to the reward, or what they call the advantages are in fact normalized rewards. So they calculate the average by batch and divide by the standard deviation. So these it seems to improve the performance. Okay, so I'll skip this. Okay, so this I hope I gave you some flavor. So I didn't to put equations or too much math in there. Give you flavor to how it is used in these LLM models. So it's a powerful technique to improve LLM models. So well-taught reinforcement learning models can help LLM models improve their reasoning capabilities, right? They can be combined with other techniques such as Monte Carlo tree search to explore and refine reasoning. So this is like another presentation, but we saw how they do it for AlphaGo, for instance. Reinforcement learning, you need rewards, right? And the better the rewards, right, the more calibrated they are, the better would be the outcome. So if they're combined, you combine them with oracles or verifiers. Oracles means that these are models, you know the truth, the ground truth, right? You know that this is correct or not. Or for instance, verifiers, we say we use it in math. So you have a program that can check that the math proof is correct, right? So then the reinforcement learning can work very well, right? Because it knows that the reward, the proof is correct, and it's going to try to change its policy, or its strategies to get to the better answer. There's no verifier if you don't know what is the ground truth, right? Then it's kind of difficult to get good rewards, right? So I think that and that's why it's used a lot for coding, math, science, like hard science, things like we have an idea, or some people can say this is correct or not correct. In some other fields, it's difficult. Like poetry, is it a good poem, a bad poem? Maybe it's more subjective, and so maybe this method might not work as well. And many things in life are not definite, right? Many things in life we don't know if it's correct or not correct. Also in the future, so all these things usually they're done before you use the model, or is done in real time, right? The post training. So we're getting close to machines that can learn in real times, and also probably like can teach other machines, right? So this is what we have this, right? So you can see like a machine can understand might think of designing a reinforcement learning models to teach other machines. Okay, so this I don't think has happened yet, but it's not too far-fetched to think that they'll be able to do that. And once you do that, you might have a loop that this machine will keep improving. So these are like exciting times for some if you like this, worrisome time for others. Okay, so I'm to stop here. So you have any questions? I'll happy to take them. Oh, uh, can you hear me, Prafula?
Yes, I can hear you.
Okay, very good. If you have any questions, please raise your hands. And, okay, I can mention too. If you find that presentation was a bit too technical, I think the Prafula has mentioned that there was an article in the New York Times yesterday or like very recently that talked about this. So it's more like so it doesn't go to too much details, but give you also a flavor of how this DeepSeek OpenAI as working. And they mentioned reinforcement learning, but it's more like a very brief overview. Okay, if you don't have any questions, I'm to stop here. The presentation is going to be recorded and I'll put it on YouTube. If you have any questions, you can put it in the Meetup group, and I'll be happy to address that. Okay, so thank you very much, and talk to you soon.